Hi, in this video, we want to take a look at the properties of the periodogram. Okay, so the big idea in this video is that we have time series data. We're going to run the discrete Fourier transform on our time series data, and we're going to use the discrete Fourier transform to analyze the seasonal components of our time series. So we're trying to pick up the periodic aspect of our time series using the Fourier transform. All right. So we're going to run through some examples from time series analysis and its applications. Here are the names of the authors. Here's our GitHub page. And students at the University of Florida can download the textbook for free. All right, so first and foremost, let's talk about the discrete Fourier transform. All right, so let's say that I have some given data points, n of them, in fact. Our discrete Fourier transform is where we're going to take our data points, multiply by e to a imaginary power, 2 pi times omega sub j times t for, same index as our data point there, then I. Okay. And that's going to be our discrete Fourier transform. Now, the omega sub j is going to be a Fourier fundamental frequency, and it's just going to be j over n. All right, now, something that's important to be aware of whenever we're talking about a Fourier transform, different packages, different softwares, different textbooks, different papers will slightly change up the Fourier transform. And the mathematical theory of what they're doing makes sense if you consider the changes that they've made across the entire scope of the Fourier transform. So the punchline of this is that always read the help documentation before you start doing Fourier transforms. Make sure you understand exactly what's happening. Now, if n is composite, that is, it's not prime and it has a significant number of factors, then we can run the fast Fourier transform. So the textbook talks about significantly or greatly composites. And so what that's just saying is that we want to be in the situation where the n has a lot of divisors. So it's very, very far from being a prime number. Preferably, we would like it to be divided by 2, 3, and 5. The smaller prime numbers. Okay, so let's look at the inverse discrete Fourier transform. Well, actually, let me scroll back up. So here is the Fourier transform. Looking good. Notice that we have a negative sign here, and our inverse discrete Fourier transform is where we're going to do something very similar, but notice that I've got different index on this. So here, my indices go from 1 to n. Here, the indices go from 0 to n minus 1, and there's no negative sign here. And this gives us the ability to take our original data, do the Fourier transform. Later down the road, if I have Fourier transform post-transformation in my hand, I can convert it back to the original data corresponding to it. And that's what the inverse discrete Fourier transform does for us. So something that is important to notice is that the scalars and the signs of the exponents in the discrete Fourier transform and the inverse discrete Fourier transform. So pay attention to where is this n, the square root of n. When I learned this material, the author of the textbook preferred to just have 1 over n instead of 1 over square root n. And notice that where the negative sign is. Different authors will move and adjust these two features quite a bit. All right, so let's go ahead and run through a code example. So let's just say I have my data points 1 through 4, 1, 2, 3, 4. I can go through, I can do the fast Fourier transform. And now just to be consistent with the book, we're going to go ahead and divide by the square root of the length of our vector. All right, so here's the discrete Fourier transform of the numbers 1, 2, 3, 4. Now I can go back and I can do the inverse discrete Fourier transform. Once again, I'm dividing by the square root of the length of the vector. And you'll notice I get 1, 2, 3, 4 again, but because we had complex in the situation, these are stored inside the computer as being complex numbers. Now, if I wanted to, I could drop the imaginary part. That would be easy. All right, and to do that, I can just use the real function, RE, in R to keeping it real. All right, so now let's actually talk about the periodogram. The periodogram is the item that we're going to use to analyze the seasonal or periodic trends contained within our time series data. So the periodogram is just going to be the square of the modulus or absolute value of our discrete Fourier transform. All right. Now, something that is important to notice is that when omega sub j is equal to 0, then our discrete Fourier transform is in fact x bar times the square root of n. Okay, well, if I go ahead and take the absolute value and square it, I can see that that means that our periodogram at 0 is n times x bar squared. Okay, we'll use that again in a moment. Now, let's think about the centered discrete Fourier transform. Well, look at this top line here for a moment. Just focus on this. Let's say that I just focus on the E business that we've got going on. And you know what? The indices go from 0 to n minus 1. So let's go ahead and do what it takes to change our indices going from 0 to n minus 1. Notice that I just factored out a little bit of this. And so now t is going from 0 to n minus 1 instead of 1 to n. And I realized that this is, in fact, a geometric sum. All right, so it's telescoping. Let's go ahead and telescope it. And then I remember that by how we're selecting our indices for this, I realize that this whole thing ends up being equal to 1. Therefore, the whole summation is equal to 0. Huh. All right, well, that's nice. So what I could do, if this is my discrete Fourier transform, right here, I could subtract 0, and that would not change the result, right? Subtracting by 0 does nothing. So let's go ahead and do that. Just we're subtracting by 0 in a funny way. And when I do it in this way, notice how I write this out. I've got x of t here. I have x bar. And I've got the e, and I got the e in the same position over here. And so, in fact, I can rewrite this as the difference between our time series data and the sample mean. All right, so what this is telling us is that if I center my time series data, that's not going to change the periodic seasonal features of my time series data. All right, so we could go with either one. It'd be easy peasy lemon squeezy. All right, so now let's go ahead and connect the periodogram to covariance. So the periodogram is the squared discrete Fourier transform. All right, so let's go ahead and write that right here. Here's the discrete Fourier transform. Take the modulus and square it. All right, now I can rewrite that as, well, here's the formula for discrete Fourier transform, and here it is again. But you'll notice that I have different indices. I have an index for t. I have an index for s. All right, well, different indices. That means I can actually go through and start multiplying this. So let's do exactly that. So now when I do this, you'll notice that, hey, that looks a lot like covariance. Huh. Okay, let's go ahead. Now, what I'm going to do here is that I notice that I'm going to have a negative s on this. Forgot to talk about this. So we've got a negative s. And okay, the reason for this is because of the complex number aspect, is that this is going to be equal to the modulus squared, because I have the complex number and I have its conjugate over here by multiplying by a negative sign. Huh, okay. So now when I go through and I simplify it here, once I get to this point, I'm going to go through, convert the exponential to addition, and then I'm going to combine like terms. And you'll notice I have the autocovariance aspect, Then I have E, and I've got a difference on the indices. Okay. So now I'm going to look at this. And I realize that I can rewrite this. What we're going to do, we're going to rewrite this in a manner that makes this look more like autocovariance. Okay, so what we're going to do, we're just going to change some things up. So instead of having T and S, I'm going to replace the S with T plus absolute value of H. All right, so now when I do that, when I replace the S, I have to go through and do some relabeling, some shifting of my indices. But if you sit down, you do the pencil and paper work, this will work out. And when I have this presentation, I realize that this parenthesis is the empirical autocovariance for a lag of H. So boom, I've got this. So now I have a connection between my periodogram and autocovariance. Now, if you think about this for a moment, if I'm taking the larger lagged values for my time series to do auto covariance, well, eventually, like I'm just going to have like the first and the last when I get a big enough lag. And what's going to end up happening is a data point of 1 for an estimator probably isn't going to be very good. So what we're going to do, we're going to modify this formula to get an empirical estimator of this. So what we're basically just going to do, instead of using all possible values that we could possibly get, we're going to just trim it down. We're going to reduce the number of lags we use in our the auto covariance of, and that is how we're going to get our estimation of the spectral density. And here we want M to be much smaller than N. All right, so now we want to talk about spectral analysis as principal component analysis. Now, I don't like using the term principal component analysis in the situation. Conceptually, I can see why the authors did this, but I would rather just say it's more like the fundamental components. So the trig or the spectral analysis basically gives us the fundamental aspects of our time series in terms of the periodic seasonal part. All right, so sine and cosine are fundamental to this. And the spectral density approximates the eigenvalues of the covariance matrix of a stationary process. So we're assuming we have stationary. For sufficiently large sample size, the eigenvalues of the covariance matrix are going to be pretty close to what they're supposed to be. So we get this connection. Well, we just figured out an empirical version of this right here. Now, realize that a covariance matrix is symmetric. Since it's symmetric, it's a normal matrix. It's a normal matrix, therefore it can be diagonalized by a unitary matrix. Okay. So also, since it's symmetric, its eigenvalues are real. All right, so let's go ahead and say that this is one of our eigenvectors. And we're going to represent G as the matrix of eigenvectors. Now, we know that we have a complete set of eigenvectors because it's a diagonalizable matrix, because it is symmetric. All right, so after I've set this up, I'm going to go ahead and let's say that Y is equal to the adjoint of G times the vector X, where the vector X is my data set. Oh, this should be a 2 right there. But the vector of my data, the entries of Y are asymptotically uncorrelated random variables with zero mean and variance of spectral density of omega sub j. Now, we know that G is full rank, that it is a square and invertible because we of the unitary diagonalizability aspect. And so if I have Y, I can get back to X by multiplying by g on both sides of the equation. So if I want x, I just multiply g by y. And so now this gives us a new relationship between x and the y we just established. All right, so now let's take a look at the expected value of our periodogram. Okay, so we're going to assume that our time series is a stationary process with an expected value of mu and spectral density of F, and it's an absolutely summable autocovariance. All right, then if I use the formula that we talked about a moment ago here, so here this is just the connection between autocovariance and periodogram. I take the expected value of both sides, and you'll notice that when I take the expected value, because it's constant with respect to t, this is no longer going to have a t after I take the expected value. It becomes the autocovariance. Okay, so now I notice that this whole thing is constant with respect to t. So I'm just going to do the natural thing I can do and replace this summation with multiplying by a scalar right here. And so now that gives me a formula for the expected value of the periodogram. Now, let's take a look at the convergence of the periodogram to the spectral density. All right, so what we're going to do, how we're going to handle this, is that we're going to let j sub n be an integer sequence such that j sub n over n is the closest fraction of the form k over n to the overall omega. All right, so j sub n over n is the closest fraction with a denominator of n to omega. All right, well, this sets it up so that this sequence of fractions is always within 1 over 2n to omega, which means that as n goes to infinity, the sequence converges to omega. Now, under the absolute summability of our autocovariance, the limit of the expected value equals the spectral density. So the absolute summability allows us to invoke the dominating convergence theorem, so that's how we're able to get this. And so we can interpret the spectral density as the long-term average of the periodogram. All right. And so we go ahead and, just take the limits as n goes to infinity. And we get our spectral density. Now let's take a look at the relationship between spectral density and variance. So what we're going to do, we're going to set omega to equal to 0, and the j sub n's are all going to be equal to 0 because that's the closest fraction with denominator of n to 0. All right, well, remember the formula we talked about a moment ago? That we know that the periodogram at 0 is equal to n times x bar squared. All right, well, I have a random variable squared, right? Huh. So is there some way that I could possibly use that? Well, so if I take the expected value of the periodogram, that's going to be n times the expected value of x bar squared. The expected value of x bar squared is almost a formula for a variance. So let's go ahead and do what we need to get a variance out of it. And we realize that the expected value of our periodogram at 0 minus n times mu squared is equal to n times the variance of x bar. And so the expected value of our periodogram at 0 converges at our spectral density at 0. And n times the variance of x bar goes to a spectral density when mu equals 0. All right, so now one thing that we are going to assume with our time series is that we have absolutely summable autocovariance. And that gives us a lot of properties to work with from our pencil and paper theoretical point of view. Now, there are more properties if I can make this a little bit more complicated by multiplying by h. And we're just going to leave that alone for the moment. We're not going to use it, except for in this one spot that we're going to use this for the distribution of periodogram ordinates. All right, so here I'm using that property we just talked about. So we have h times our autocovariance, absolute value, added up from negative infinity to infinity, is a finite value. Here is our moving average series representation of our time series. And the coefficients of the moving average aspect is absolutely summable. W sub t is IID 0 with a constant variance. Notice I did not specify the distribution. And our Fourier frequencies are between 0 and 1/2 for all m, and they are distinct. And our Fourier frequencies are converging to a particular frequency that we want. And spectral density at the Fourier frequencies are always positive. Then, so if all of this is a long list. This is making me tired just to even like look at it. Gosh, this is a long list. If all of this is true, then 2 times the periodogram divided by the spectral density converges to chi-squared degree 2 in distribution. All right, so if that's true, then this gives us a way of getting a confidence interval for our spectral density. And so we just invoke exactly what we've got. All right, so now one thing that we're going to want to do before we start running these calculations is that we're going to want to center and detrend our time series. So often trends are present that should be eliminated before we compute the periodogram. All right, so what's going to happen is that if I try to do the periodogram and there is a trend, the system is going to assume that this is a reflection of another trend, another periodic aspect. And so what will happen is that it's going to interpret that overall trend as a half cycle. And so we're going to get, we're going to mess up our results. And the results that we're looking for are going to get obscured. So what we're going to do is that we're going to center our data, and we're going to detrend our time series by one way would be to just subtract off the linear trends. If we have a more complicated trend going on with our data, let's say that there's like a polynomial aspect on x with respect to t, or there's something more exotic like non-parametric modeling, then what we could do is just use the appropriate model to subtract it off. All right, so discrete Fourier transform, if we can, we prefer to use the fast Fourier transform. But the fast Fourier transform requires that we have numbers, the number of observations are extremely non-prime, that we want them to be highly composite. All right, well, what we're going to do is that we're going to add zeros to our data until we have a number of observations that's divisible only by 2, 3, and 5. Ideally, we would just have a power of 2, honestly. So here we're talking about padding our data, and this will be after we detrend it, after we center our data. So I pad the data. Now I have a new number of observations, and we'll call that m prime. So let's run through an example of this. Let's use the SOI and the recruitment data sets. So here, this is the number of observations we have, 453. Now, I'm going to do the prime factorization of this, and we see it's 3 times 151. Okay, it's not prime, but it's pretty close to prime. So what we're going to do is we're going to use the next n function to pad zeros until we get a number we would much rather work with for the fast Fourier transform. All right, and it chose to do 480. Okay. And what are the prime factors of 480? Well, I see a bunch of 2s, a 3, and a 5. All right, so now let's actually run our periodogram for the SOI and the REC data sets. And we'll see immediately that there is like a peak around 1/4 and 1, and that's true for both. All right, well, because of the nature of the data, what we're talking about, this once every 4 years aspect, so 1/4 corresponds to 1 every 4 years, this is being called the El Nino effect. And so the bandwidth around 1/4 indicates that El Nino is irregular. It's not very consistent, but it occurs on average every 4 years. And that's from things being kind of like wide, not really being a hard, firm trend. And so here are the details of this. Now we're going to compute the confidence intervals for our stuff. And so now I'm invoking that chi-square distribution. And I'm going to go through and just compute confidence intervals for myself. And we'll notice that the annual confidence interval is really wide. But if I look at it, I'll realize that the lower bound of that confidence interval is larger than all but the El Nino estimates. And so this indicates that, you know what, I've got something good, even though it's very, very wide. We can also run the same analysis on the El Nino aspect, that the confidence interval is very, very wide. There'd be reason to have less faith in it. And now for the recruitment time series, we're going to do the same thing. We'll compute the confidence intervals. All right, now let's take a moment and think about this so that this fraction converges to a chi-squared degree 2 in distribution. So that leads to a natural approximation that we can say that for a sufficiently large data set, that our periodogram is approximately 1/2 times spectral density times a chi-squared random variable. Okay, well, our chi-squared has an expected value of v and variance of 2v. So invoking that, working with this, we can see that the expected value of our periodogram is equal to the spectral density, and the variance of our periodogram is equal to our spectral density squared. Notice that the variance of the periodogram does not go to 0, and thus the periodogram is not a consistent estimator of the spectral density. The solution to this dilemma can be resolved by smoothing the periodogram. All right, well, that's all I've got for you. Life is short. Do math.